This is a dramatic reading of 6th Snarky Puzzle Answers, a blog by the Stand-Up Physicist available at science20.com. The 6th Snarky Puzzle Answers leads off with a little bit of a controversy. This comes out of actually two different snarky puzzles. The first one was on September 20th in the blog Deriving the Maxwell Source Equations Using Quaternions 2 of 5. This blog was too long. Make the author, me, suffer! Let him go out and figure out why b squared minus e squared is invariant under a Lorentz boost. And then on October 4th for the Deriving the Hypercomplex Gravity Field Equations 4 of 5 blog, the snarky puzzle went, show that small b minus small e squared, those are the hypercomplex fields that show up in that proposal, and it is very similar to the E and B fields of EM, only they're kind of like the symmetric counterparts. Things that you'd extract out of a symmetric tensor, say, than an anti-symmetric tensor. But go to the blog, of course, for more details about that. But show that thing is invariant under a Lorentz boost. I'm pretty sure I did that calculation once. So here's the background. The short answer is that both the EM b squared minus e squared and E dot b are invariant under a Lorentz boost. Everyone knows that. And despite how that question was phrased, the difference of those hypercomplex field equations, b squared minus small e squared, and that's not Lorentz invariant. The detailed calculations were done in a Mathematica notebook that if you go to the blog, you'll find a link for it. And two commenters on that October 4th blog were able to spot that error in the question. They were right. So, you know, in my first job out of MIT, at MIT, I worked as a lab technician. I didn't really think too much about the big picture sort of thing. I mean, that's what the principal investigator did. You know, writing grants involves a lot of big picture thinking. So what I focused on was thoroughly asking a question, making sure that there were like plenty of controls. And it was really quite a bit of fun to use that same kind of attitude to resolve this issue. So here's the experimental setup. We've got two 4 vectors that are going to be used. One is called the current density J, and the other is the 4 potential A. And there's also the 4 derivative del, which transforms like a dual of a 4 vector, which is a mirror image actually of how the 4 vector itself transforms. Now we're going to do 3 different operations to those 3 different vectors. One is nothing. The second is a 3D rotation around the z-axis, and the third is to do a boost along z. Now, nothing is easy. No, really. Doing nothing for that first set is really not a challenge. You just write it down. The 3D rotation, well, that does require just a little bit more math that goes back to the 1850s. And quaternions, you know, remain a one-trick pony in most folks' eyes for doing 3D rotations. You know, they're just the best in the business. You've got fewer math operations, it's easier to correct for errors, and there's this no gimbal lock problem. Now, one needs what are called unitary quaternions. And for the rotation around z, just use oh, here's my whole description of it. How to do 3D rotations. You've used this unitary matrix that goes cosine of alpha, 0, 0, sine of alpha. Okay, and the norm is unity because cosine squared plus sine squared, that equals 1. Oh, a little bit of high school math. You know, so to do a rotation, you escort any old Joe quaternion, I'm calling this one R, on either sides by one of this U things and its conjugate. And when you do that, you'll notice that the rho and the JZ guy, they're left untouched. And it's just this X and the Y terms that have cosines and sines. One of them's positive, one of them's negative. Okay, it's confusing, but it's not that it's impossible to believe as might be true. It is, okay? And that's all using pretty standard kind of a quaternion approach to it. Not that complicated. And of course you can do the same thing for the for potential A and for the dual 4-vector thingy del. And those types of repetitive details are done in the Mathematica notebook. I mean, repeating yourself is easy using a computer. Now, the way to do a boost along the z-axis using quaternions is just not well known. As far as I can tell, such a trick is not actually in the literature. No. This means that quaternions can actually be ignored by professionals for a valid reason. You know, it's just these Lorentz boosts are just too important. So that's why I said I got to figure out how to do this. And I figured, well, why don't I just do a variation on the 3D rotation machine? So you need to type in hypercomplex functions, you know, and so this is the idea. Now that hypercomplex thing, I've got the cosh of a beta thing, 0, 0, sine h, and so you just put it into exactly the same structure as the 3D rotation, and well, it doesn't work. Okay, so just go and fix the problem. Just search for a little while, and it's not that hard. You take the two hypercomplex guys and hit it against that B, take the conjugate, minus conjugate H guy, B, with a conjugate there, divided by 2, and wow. Where did you figure that out? I just kept on trying things till they worked. I noticed what was wrong. Oh, how do I fix it? That kind of stuff. Very much the experimentalist kind of attitude. Don't say, what is the big picture? Just fix the problem. You know. Okay, and so when you do that on the good old J thing, you'll notice that the X and the Y, the JX, the JY, they're left alone. Okay? And it's the outside guys this time that get mixed around there. One of them gets, you know, well, actually they both get coshes and sine h's, and actually they do have the same sign this time. But I did it using quaternions. You don't have to do it that way. It can be done that way. We say it's the same up to an isomorphism, which is to say that if somebody comes along and says, I've got to do it this way, it's like, fine. We end up at the same spot, and so let's be at peace. All right, so similar boosts can be done for the potential A and the dual of del, and those are in that notebook. So we've got, really, so what do we got here? We've got these 3 players, the J, the A, and the del. Well, we've got doing nothing, the good old null, a rotation, and a boost. And then we're actually going to have multiple ways to form products. One is going to be the quaternion product, okay? And the other is going to be this hypercomplex product, and that I symbolize with the box times symbol. So I'm glad I have a computer, because that's a lot of stuff to do. So, you know, that hypercomplex thing can also, product can also be called a basically the Klein 4 group in action, or quaternions without any minus signs, if you want to figure out what the rules are. And these are the target products. These are the things I'm trying to calculate 3 different ways. Well, the way that it's written right there, and then after it gets rotated around Z, and after it gets boosted along Z. It's like, whoa, well, that's a lot to do. Okay. And now, if this is invariant under a if these guys are invariant under a Lorentz transformation, then the first terms out of those products are going to be the same, whether you do nothing, whether you do a rotation, whether you do a boost. They're always going to be the same. And so this approach really is kind of conceptually simple. You do your rotations, you do your boosts in these different situations, and then you compare the results. And there's just a large volume of detail, all of which has to be done perfectly. Now, for 300 smackers, 3 bends, big bends, you can get Mathematica Home Edition for those who are outside of academia, inside their basements. Okay, which is what I've done. And Mathematica certainly does not ensure success, as calculations can be set up incorrectly. And you can have typos. The key to doing a good experiment, though, is having lots of controls. So I knew, for just as an example, that all of the first elements of these guys are going to be the same. So if I just take J and the quaternion product with A, or I rotate both J and A, or if I boost it, both the J and the A, or if I take this hypercomplex product and take a conjugate in there, I mean, every single one of those 6 has to be right, has to be the same. The first term. The 3-vector part, they're always going to be different. They're going to be different in ways that, well, we know. We go ahead and calculate it. Okay. So that is the control for all the tools I need in this experimental setup. It's got rotations, it's got boosts, it's got conjugates, it's got quaternion and hypercomplex products. Now, I also knew that that those lines 3 and 4 that look much longer and more complicated, those actually have to be invariant too. The reason is that one of those is the b squared minus e squared, sorry, the b squared minus e squared, and and e dot b. Now, when you do e dot b, you actually find out that one evaluates to 0. Everybody agrees to 0, and that's kind of what's going on there. So that really leaves the answer relying on what happens to that final guy. That final guy, that's essentially the one experimental dude we have in this exercise. Just that one. And it turned out that when you did the boost and you did the rotation, the scalar wasn't the same. So it's not like EM, darn it. So what does that mean in our discussion section here? Well, the smarties are going to say that I really just wasted a lot of time proving what should be obvious. Well, from my history, I really just prefer a thorough calculation, since it really can point out assumptions I might be making along the way. Now, does this result mean that the hypercomplex gravity proposal has taken a bullet to the head? Well, you'd want to know what other equations, break this global Lorentz symmetry. I went out and did Google. I can't knock on a colleague's door and say, do you know? No, I had to use the old Google. And it said, well, two examples would include general relativity, Einstein's theory for gravity, and loop quantum gravity, which is actually kind of the same thing in a way. So that's perfect. I mean, it's absolutely perfect. We might get into some kind of fight over, global versus local symmetry breaking, and but at least the hypercomplex gravity field equations are hanging out with the right kids in field theory, the ones that do gravity. So I've got this property that also general relativity has. That's pretty good. All right, now on September 13th, I had the Deriving How to Derive Field Equations blog, and here is the Snarky Puzzle out of that. So this one is straight from the start of Chapter 19 of Feynman's Lectures on Physics, Book 2. And he writes up on the board, sort of thing. So here is the path integral for a ball in a gravitational field. See if you can spot Newton's law of gravity in there. And I just showed it right down below there. So the answer is, basically MA equals minus MG. Even if you have no calculus, you can go, oh, well, imagine he took the 2 down, and then the other one, he just wiped out the X kind of thing. Yes, there's a lot more math behind it, but you could almost guess that result. All right, so what Feynman really wondered about was how did nature do that sort of calculation on the fly? Well, answers to the simplest of questions like that still remain out of reach. All right, so on September 27th, I had the Deriving the Maxwell Homogeneous equations using quaternions, 3 out of 5. And here was the Snarky Puzzle. Take one of the quaternion derivative ways of writing E and B and square it. Notice that the scalar Lagrange density will be able to generate all 4 Maxwell equations via the Euler-Lagrange equations. Correction. No. That does not actually work. Okay. And I gave an extra bonus point problem, which was math overdose, scary as shit bonus problem, which was do something with a 3 vector that's generated out of these, crashing these quaternions all together. And so I didn't get an answer because, the poorly formed question. It's important to recognize that. Basically, it's like 1 a.m. or something like that. I had that idea, and I said, oh, look, there's an E dot B in there, and there's an E squared, and there's a B squared. Isn't that wonderful? Well, not really, because the Maxwell source equations need the difference of 2 squares, but those guys have the same sign, so they really can't be used to generate the Maxwell source equations. So the question was just flat out, bogus. I was able to do a bit of math on the overdose problem, which was to say, okay, instead of grabbing the scalar, the first part, switch your focus over to the second one, put it through the Euler-Lagrange machinery, just see what happens. And I got a whole bunch of partial derivative things, and I looked at it, and I don't get it. Oh, it's one of those things that I probably have to look at for a few weeks and read up and Google around and see if it was at all relevant to anything. And I just don't have the time to kind of to have really gone through that. It's doable in theory. All right, now on October 11th, we did Deriving the Unified Gem Field Equations 5 of 5, closing out the series. And here was the Snarky Puzzle. I doubt it is meaningful, but do the sum of the gauge-dependent Lagrange densities instead of the difference. Practice, practice, practice. Someday these equations may solve a deep mystery, or not. So the background is that I just want to be complete when I do my mathematical physics. And it struck me that working only with the difference of the gauge-dependent fields was not complete. So the answer is that you only get the cross terms, which have contributions from all four positions to be found in the four derivative or the four potential. And, you know, you just kind of run that through the Euler-Lagrange equation, and one of those four things just bows out. So we see that, you know, these are kind of mildly amusing. I mean, the first equation has a row, and then it dodges anything like a phi or time derivative. And the second row has a jx, good for it. And then it doesn't have no ax or any derivative with respect to x. And quite frankly, I don't know what that means. It's just kind of cute. So there's no real reason to think that this particular set of equations should be taken seriously at this time. We'll wait for some time in the future. All right. Thank you very much.